Good morning, everybody. Welcome back to non-Euclidean geometry. Plan for today is I've got a quiz for you on instance geometry, and then we are going to move into our next packet and start talking about betweenness geometry, focusing on adding a few new definitions, as well as 4 new axioms that are going to give us some new geometric ideas to play around with. Got my usual office hours today and Wednesday after class, and from 2 to 3, tomorrow at 11, and from 1 to 2. And as far as homework goes, keep in mind you all have a homework 3 due Friday. And no, I have not graded the homework 2 yet. Still working on those. Any questions or comments before I pass out today's quiz? Yes, Elaine? All right, you know what? I'm going to be nice. Today you can have a bonus trick. Give you one before, one after. What do you get if you start with 1 rabbit, and then you add to that half a rabbit, a quarter of a rabbit, an eighth of a rabbit, a 16th of a rabbit, a 32nd of a rabbit, and so on? Top 2 questions. And you should end up with 2 rabbits, but practically speaking, this isn't really possible to do unless you're willing to split hairs. All right, go ahead and put everything away. It is quiz time. Just so you know, this one has a backside. The backside just has the instance geometry axioms written out for you. They're also on the board if you prefer to use those. The only questions you have to answer are on the front side. Feel you are finished. On the back, draw a picture of Dr. Trelawney disrupting my class by being too noisy. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. All right, question. Why is it generally a bad idea to try and teach horses analytic geometry? It's because it's not a good idea to put a cart over the horse. Okay, so the last packet we talked about Hilbert's axioms for instance geometry. We looked at what does he think the definitions for points, lines, and the idea of a point being incident to a line should satisfy. We looked at his, by looking at the 3 axioms of instance geometry. And then we looked at a bunch of different topics of things that made models of instance geometry, things that did not form models. What does it mean for 2 models to be the same? What can we sort of prove? What propositions can we prove using the axioms of instance geometry? But here's the thing. Instance geometry, it only gets you so far. If all that you can do in geometry is talk about points, lines, and whether or not a point is on a line, we've seen that that can lead to some interesting stuff happening, but it doesn't get us a lot of things. It doesn't give us any idea of what does it mean for a point to be between 2 other points on a line. What does it mean for segments or angles or whatever to be congruent? What does it mean to have some notion of continuity to our design of geometry? And so what we're going to be doing now is we're going to be adding in some new axioms and some new definitions that are going to allow us to extend our notions of instance geometry to include some ideas of what does it mean for a point to be between other points. And so, in between this geometry, we're going to keep everything that we had from instance geometry. We're still going to have the same 3 undefined terms that we started with, and we're still going to be assuming in our new model of geometry that the instance axioms hold true. So we still want IA 1, 2, and 3. I'm going to add a new undefined term here, and that is the idea of what it means for point B to be between 2 other points. And if point B is between A and C, we're going to denote this by writing A star, B star, C. That's going to be our shorthand to say that point B is between points A and C. For collinear points, A, B, and C. Megan, you remind us, what did it mean for points A, B, and C to be collinear? Yeah. A, B, and C are all points that are going to be collinear if they're all incident, if there exists a line to which all 3 or more are incident. And so now, we're going to add this new undefined term that depending on how we define it can lead us to different models. And that's going to be the notion of, if you have three collinear points, what does it mean for one of those points to be between the other two? So if I were to draw a picture, Shane, what would you expect your intuitive idea of betweenness to satisfy with this picture if we wanted to have a point B that was between A and C?
I guess it's incident between, or what's that? Incident between.
It's hard to use good language here.
Yeah. I guess one way you can do it is equidistant from both points, A and C.
Ooh, something that's equidistant. So would you want that point to be between A and C?
A point equidistant incident to the line AC.
Oh, okay. What do you mean by equidistant?
Equal distance among both points A and C.
What is this distance that you speak of?
I don't know.
Alright, I'm done bullying you for now. Yeah, so intuitively, we're going to mean a point that does something like this. We're not actually going to intuitively require the definition that is going to fit our intuitive one eventually is not necessarily going to require any notion of equidistance, because we're not going to have any notion of distance until we get to the congruence axioms in the next packet. But this is one I want you to be intuitively thinking about when you think of what does it mean for B to be between A and C. Of course, we're going to see some models where this sort of behavior occurs. We're also going to see some models where maybe your definition of betweenness is going to be very different than your intuition, just like we saw in instance geometry. So we're going to have this definition. We're going to have this undefined term, though, for now, of what does it mean for a point to be between two other points. And eventually we're going to have four axioms that we want this betweenness term to satisfy. So before we get to any of those, though, I'm going to come up with some more definitions. Because once we have a notion of betweenness, suddenly it makes sense to start talking about terms like rays and angles and 2 points being on the same side of a line. Things that we couldn't really define just using our terms of points, lines, and incidents, because we didn't have the language at the time to talk about what does it mean to have a ray as being part of a line. But now that we have some notion of betweenness, once we know what our betweenness is, we can have these other definitions that'll then have concrete meanings once the idea of betweenness has concrete meaning. So here's going to be our new definitions for the that we want our idea that are going to come about as a result of having a notion of betweenness. So first of all, this one doesn't need betweenness, but given points A and B that are not equal to each other, we're going to define the line AB notationally by having AB with a sort of double arrow above it. And that's just going to be the unique line incident with A and B. And we know that that if A and B are distinct points, there should be a unique line that's incident with both from instance axiom 1. In all of our models of betweenness geometry, we're still going to be assuming that the incidence axioms are true, including incidence axiom 1. So in all of our discussion of betweenness, we're going to assume that given any 2 points, there is a unique line between them, And we're going to start calling that the line AB with this, using this symbol, AB with this double arrow over it. Similarly, we can say that the line segment AB, and here we'll write AB with no sort of arrows above it to refer to the fact that we're discussing a segment, is the sum of all points C incident to AB such that one of three things happens. Either C is between A and B, or C equals A, or C equals B. So in other words, in this picture, we would say that the set of all points between A and C, in this case, including as well as A and C themselves, because typically when you talk about a line segment, you want to include the endpoints. A, C, and everything between A and C is going to consist of the line segment, A, or in this case, AB, I guess, in our definition, or AC in our picture. Instead, with line segment, we couldn't actually define this just using our terms from instance geometry. We could certainly talk about the line that passes through A and C, but we didn't before today have any way to distinguish between, say, points like B and here that we would want to include as part of the segment, and say, maybe some point out there that we probably would not want to include as part of our segment. Any questions or comments? So next up, we can define array pretty similarly and say that the array, in here, we'll say AB with a little an arrow only going one direction on it, A in the direction of B, is the set of all points C on the line AB such that one of four things happens. Either C is between A and B, B is between A and C, C equals A, or C equals B. So this one, I think, is going to require a little bit of a picture again. So if we have a line A, let's say here's going to be our B. So if we want to talk about the ray emanating from A in the direction of B, meaning everything going here and out, we have to include several different types of points. We want to make sure that we get all the points that would sort of form this ray extending forever in one direction, at least intuitively. We need to get A and B. We need to get points C that are between A and B. Call this point C1 that we would like to include. And we also want to include points that make B in between A and C. So C1 would be an example of this sort of point. C2 would be an example of that sort of point. And then A and B we want to include as part of the rays going from A and B. So once we know what our between this is, that's going to give us our rays. Hey Elaine, if we have two rays and they're emanating from the same point, what are we going to get from that?
An angle.
An angle. So you can also say that given distinct points A, B, and C, the angle BAC with vertex A is the set of points on either the ray AB or the ray AC. So if this is our point A, this is our point B, this is our point C. We want to include everything on the ray emanating from A passing through B, and we also want to include everything on the ray emanating from A passing through C as well. Just like with Euclid, our angles are not defined by how much space is between the two rays. It's the two rays themselves that are going to define what we're going to refer to as an angle. And finally, our last kind of set of new definitions that we're going to want to work with is the idea of, given 2 points and a line, what does it mean for those 2 points to be on the same side or opposite side of that line? So let's see. We'll draw a picture out here. So this is our line L. Let's say this is A, this is B, this is C. Hey, Steph, are A and B going to be on the same side of L or on opposite sides of L?
Same side of it.
Why does your intuition tell you that?
Because they're together on top of L.
Because they're together on top of L.
Yeah.
Okay. Nathan, would you say that your intuition tells you that A and C are on the same or opposite sides of L?
Same, no, opposite. I was looking at the wrong one.
Yeah, sorry. Just everything below this line.
Opposite.
Opposite. Why is that?
I think if L extends in both directions, then they're on other.
It's hard to say. It's like intuitively, it's like, yeah, clearly A and C are on opposite sides of the line L. Like one's above it and one is below it. In the case of A and B, they're both on the same side of L because A and B are both above L. Of course, we don't have any notion of above or below. And in fact, if I were to draw L to look like this instead, then above and below would lose all meaning. Jared?
Oh, I was just wondering if we could talk about line segments. And,
How so?
well, the line segment AB doesn't have any points in common with line L, but the line segment AC does.
Yeah, Zeus. AB doesn't intersect L at all, whereas AC definitely has a point of intersection here. So you think we could use that as a definition of same and opposite sides?
Yeah, something like that.
In fact, that's exactly what we're going to use. So our definition of same and opposite sides, since we don't really have any, again, all that we have is some notion of betweenness, but betweenness doesn't necessarily, for collinear points, but not a notion of above a line or below a line. We can actually define same side and opposite side of a line by saying if L is any line, and A and B are not incident to L, then we can say that A and B are on the same side of L if AB does not intersect L. And they're going to be on the opposite sides if the segment AB does intersect L. So in this case, we would say A and C are on opposite sides since the segment AC does intersect with L, whereas A and B are on the same side because the line segment from A to B does not intersect with L in any way. Of course, this is trying to come up with a picture that satisfies our intuitive understanding of how we feel betweenness should satisfy, which is why Steph and Nathan, I think the two of you were having so much trouble talking about why you felt that A, B, and C were on same or opposite sides of L. But Jared, I think your proposed definition is actually going to work quite well for our purposes, and that we can sort of, now that we have a definition for a line segment, we can use that to talk about what it means for 2 points to be on opposite or same sides by saying if you take the line segment between those 2 points, whether or not that segment intersects L is then going to tell us the relationships of those 2 points vis-a-vis L. They're on the same side or opposite sides. Any questions or comments? Okay, Jack.
Yes.
We have some notion of betweenness. Before you flip the page, do you have anything that you think our betweenness idea should satisfy if you want betweenness to work the way it intuitively does? So in other words, what would be some properties that we would like for betweenness to have to satisfy?
Maybe some kind of, like if this point is between these 2 points, and like this point is between these 2 points, then like one between the two between points is between like 2 other points.
Ooh, okay, some sort of idea of transitivity of betweenness working out. That's interesting. That's not actually going to be one of our axioms, but that will be a proposition that we can prove from our axioms, I think. Anybody have any other intuitive ideas for what they would like for betweenness to satisfy?
I guess, could we say that for every line where there are 3 points of instance, that line logically one must have to be between the other?
If you have 3
Yeah,
points,
they're all unique like points. If they aren't the same point, but they're 3 separate points incident on the same line.
So congratulations on successfully predicting betweenness axiom 3. Betweenness axiom 3 is going to tell us that given any 3 distinct collinear points, exactly one has to be between the other 2. Cindy?
Okay, well, I guess it's probably closer to his brother saying you can't have it where like B is between A and C, but then A is also between like B and C. Like it has to be.
You can only have one of those? Yeah, I would say that's definitely something that would be covered by saying exactly one point has to be between the other 2. You can't have A between B and C, and also B between C and A. Right?
Given any 2 distinct points on the line, there has to be a point between them.
Ooh, given 2 distinct points, there has to be a point between them. So you're leaning right into something you wouldn't have happen that's going to guarantee we have infinitely many points if there exist at least 2. That's going to be part of betweenness axiom 2, in fact. Any other intuitive things you would like for betweenness before we move on to looking at the betweenness axioms? Yeah, I think what you all are saying are pretty reasonable things. All of that is stuff we're going to include as part of our axiomatic system, except for Jack, what you proposed, which will be something that will have to happen as a result of our axioms, but we're not going to explicitly state it. So here's our 4 betweenness axioms that Hilbert came up with. Just like how the incidence axioms were things Hilbert wanted any definitions of points, lines, and incidents to have to satisfy. These are going to be things that, if we have a model of betweenness geometry, our definition of betweenness will have to satisfy in conjunction with our other undefined terms. So right off the bat, Hilbert cheats and includes 2 axioms in one. So betweenness axiom 1 is going to say that if B is between A and C, then A, B, and C are all distinct. And B has to be between C and A. So in other words, betweenness is a symmetric sort of idea, that if you have that point B is between A and C, whatever that means, you should be able to flip it around and say B is also between C and A. So you can't have one point be between the other two in one way but not another way. It has to work both ways or not at all. And also, if B is between A and C, then they all have to be distinct, meaning you can't have a point B between itself and something else. So our second one, and this is going to be, Megan, with kind of what you said, but also saying a little bit more. Between this axiom 2 says, given any D points, D not equal to D, there exist points A, C, and E on the line passing through B and D. Again, we know there's exactly one line passing through B and D by incidence axiom 1. And such that B is between A and D, C is between B and D, and D is between B and E. So in other words, if we have some line, and if B and D happen to be points on that line, then we can always find, as Megan said, some point C in between B and D, but we can also find points on either side of B and D intuitively. We can also find some point A that puts B in the middle of A and D, and we can also find some point E that puts D in the middle of B and D. So Megan, I think what you had proposed is that a point C has to exist between B and D. Hilbert's actually going to say something stronger than that, which is not only do you have to have a point in the middle, but you also have to have points on either side of B and D. Meaning points that make B in the middle and points that makes D in the middle.
So then does that mean that for like any model that we have in the system, like it has to be an infinite, like it has to be an infinite number of points?
I don't know, does it?
I think. Like it doesn't say so explicitly, but then like
Is that implied?
I think so, because if you have that, then you have points A, B, C, D, and E, and then you can pick C and E and do the same thing.
Find points on either side?
Yeah.
Okay, so that'll all, well, B will be a point that's on one side of C, D will be a point in the middle, but that would give us a point F that would have to exist.
And then if you kept doing that, it would have to be infinite, right?
And then you could apply between this axiom 2 to find a point between E and F, a point between B and E, a point between C and D, between B and C, between A and B, and then apply it again to get points that are in between all of those. Well done, Sydney, you've successfully spoiled my activity. Go on the next page. But yes, I think that what you said is absolutely correct. Betweenness axiom 2 is going to imply that any model of betweenness geometry, if you have any line, since any line has to have 2 points by instance axiom 2, to start with, betweenness axiom 2 will then guarantee that line has to have infinitely many points. Let's go ahead and include that here then. By betweenness axiom 2 and incidence axiom 2, every line must have an infinite number of points. Actually, I'm going to add in here betweenness axiom 1, the part where between this can only apply to distinct points. Because otherwise we could be cheeky and say, let's find a point between B and D. I'm going to choose B. Now let's find a point between B and B. I'm going to choose B. Oh, but we also need a point between D and D. I'm going to choose D. And a point between B and D. Oh, how about D? We could be cheeky and say, without between this axiom 1, just choose the same points over and over. But you're absolutely right, Cindy, that in conjunction with between this axiom 1, this distinctness condition, we can say that every line is going to have an infinite number of points. Yeah, that's good. Thank you. Any other questions about between this axiom 2? So right off the bat, by the way, we can say that some of our models, a lot of the models of instance geometry that we were looking at are no longer going to be able to hold up. Like our models with 3 points, with 4 points. We had several different models like that we talked about last week. Those models aren't going to be able to satisfy between this axiom 1 and 2, no matter how we define between this for those sorts of models, for those models. Axiom 3. Jane, I think you basically said between this axiom 3 already, which is given any 3 points on a line, exactly 1 has to be between the other 2. If A, B, and C are distinct, I'll say distinct collinear points, exactly 1 of these points must be between the other 2. And Sydney, I think that also encompasses what you had proposed earlier, that if B is between A and C, then A can't be between B and C can't be between A and B, because of this exactly 1 condition. And finally, between this axiom 4 is going to relate to this definition that Jared had proposed of what does it mean for points to be on the same or opposite sides of a line. And what it's going to say is that for every line L and points A, B, and C not incident to L, we could say, first of all, if A and B are on the same side, and if B and C are on the same side of L, then A and C have to be on the same side of L. So in other words, we draw out a picture. I'll draw one out over here. Basically, what we're saying here is that if you take the line segment from A to B, and that doesn't intersect L at all, and if the line segment from B to C also doesn't intersect L at all, then the segment from A to C also cannot possibly intersect the line L. Something that may feel intuitively obvious. Yeah, duh, A and B are on the same side and B and C are on the same side, then A and C have to be on the same side. This is actually going to be one of the more powerful between this axioms. This notion of being able to say, if this segment doesn't intersect a line and that segment doesn't intersect the line, then this segment also cannot possibly intersect the line. That's going to be very nice with regards to being able to say, prove things by contradiction. A lot of things you can prove that end up contradicting between this axiom 4. You assume the opposite. So that's only part A of between this axiom 4. Part B is pretty similar. It's going to say that if A and B are on opposite sides, of L, and B and C are on opposite sides of L, then A and C must be on the same side of L. So in other words, if we have a scenario where here's our line, here's A, here's C, here's B, we can say that if the segment from A to B does intersect L, and if the segment from B to C also intersects L, then the segment from A to C can't intersect L. Would be another way to write that out. If A and B are on opposite sides, and B and C are on opposite sides, then A and C are on the same side. And with that, I'm going to leave you with a quote from Treebeard from Lord of the Rings. Besides, I am on nobody's side, because nobody is on my side. Nobody else cares for the trees as I do. Okay. So when we come back on Wednesday, today was a lot of kind of throwing up definitions and axioms on the board so we could discuss them. When we come back on Wednesday, we'll start looking at some models of betweenness geometry and start proving some propositions. Things like what Jack was suggesting earlier that we'll have to follow as a result of the instance and betweenness axioms in conjunction. Hope you all have a good rest of your day. I will see you all on Wednesday.